Here are some quick notes on the Saha equation to accompany Chapter 4 of To Build a Star. So we just introduced the Saha equation in the book and just start using it, and you might wonder, when does this thing actually apply? Like, can we always use it for every stellar astrophysics scenario? So let's take a look at the equation. What is it? You have, for instance, the fraction of nuclei that are in a particular ionization state relative to another. So for instance, first excited state, or not first excited state, sorry, ionized, singly ionized versus neutral. And this depends on the electron density of the environment. You have some degeneracy factors here, so how many states do you have for a given energy level of your nucleus? And then you have this exponential factor here. And one thing you should keep in mind is that because you have a difference between these two energies and the exponent, that is essentially, it's not essentially, it's mathematically equivalent to, and it comes from, in fact, the ratio of two exponents. So what these exponents are is they tell you the probability of being in a particular state. So if you assume that Boltzmann statistics are valid, then your probability of being in a given energy state is going to be proportional to the energy of that state divided by kT. So K is the Boltzmann constant there. So we're assuming that Boltzmann statistics are valid, that you have a classical scenario and not a degenerate environment. So this is only going to be true, you're in a non-degenerate environment, if the density is much less than the so-called quantum concentration. So the quantum concentration, you will solve this in the homework, but basically it's the volume that a particle would occupy if its extent were only the de Broglie wavelength. And if your density is much less than this, then you are in a non-degenerate environment. And you'll find that the quantum concentration, it works out to be this business here. So all this stuff, including the 3/2 power, that is your quantum concentration. So also in the homework, you will work out what this is. You can plug in the conditions for the solar photosphere, and you find that the density of the photosphere relative to the quantum concentration for those environment conditions, so that electron density and that temperature, is going to be around 10 to the minus 6. Instead, if you go to the solar core, which is a much higher density but also a much higher temperature, you'll find that your density relative to that quantum concentration for those conditions is like 100, right? So the density is not only much less than the quantum concentration, it's actually quite a bit higher than it, which is interesting. So if you were to then use the Saha equation for the solar core, you would find that supposedly much of the core of the sun is not ionized, which is a little bit ridiculous. The core of the sun is pretty much fully ionized. So this Saha equation just does not apply there because Boltzmann statistics really aren't applying in that environment. So obviously we cannot use the Saha equation for the solar core. You will do an interesting homework problem related to whether or not you could use the Saha equation, for instance, for white dwarfs or neutron stars. Another conclusion here is that the solar core must be partially supported by electron degeneracy pressure. So because the density is much greater than the quantum concentration, we're in a degenerate environment, and so there's going to be a contribution to the core pressure from electron degeneracy, which is kind of neat. I mean, probably to now, if you've thought about electron degeneracy at all, you've probably thought about it in terms of white dwarf stars, for instance, and actually it even applies to just our regular old sun, which is kind of cool. And what's important to mention is it doesn't mean that the solar core isn't ionized. So as I mentioned, if you just blindly used the Saha equation, you'd find that a decent chunk of the core is not ionized. That's not the case. What this means is that the photons, which in this case are the ones doing the ionizing for the assumption in the Saha equation, they're not the ones doing the ionizing when you're in a degenerate environment. It's actually the pressure. High pressure environments cause ionization. That's kind of cool. Okay, so let's put the Saha equation to use. What can we use the Saha equation for? And you can use it for stellar abundance ratios, as I'll show here. So for instance, let's say you observe the sun, and if you look at the sun, this cartoon's kind of a joke, but the lines, many of them are actually real. If you look at the sun, you'll see absorption lines, for instance, from calcium, iron, hydrogen, many other elements. And looking at the width of the lines, you can infer the number of absorbers that you have. You can figure out how many, for instance, calcium ions do I have which are in the singly ionized state that are absorbing photons. You can also, from the width of a line, for instance, figure out how many hydrogen absorbers do I have. And it's always going to be relative. It's not going to be an absolute number. So for instance, from line widths, you can measure that you have 400 more absorbers of singly ionized calcium compared to absorbers that are in the Balmer state. So the question is, does the photosphere then have 400 times more calcium than it does hydrogen? And of course not. That wouldn't make any sense. We know that the sun is mostly hydrogen. So the important thing is here, we need to know the fraction of all hydrogen that is in this first excited state, which is what, when you absorb a photon, leads to the Balmer lines. So what fraction is in the first excited state for neutral hydrogen, and what fraction of calcium is singly ionized? That's what we need to know. And we can use the Saha equation to figure this out. So this is something you'll work out in the homework, where you will figure out how to calculate what fraction of hydrogen ions are neutral and in the n equals 2 state relative to the total amount of hydrogen. And you don't do it in the homework, but you have the machinery set up at that point to also calculate what fraction of calcium ions are doubly ionized. And that is, this is shown here. So what we have is basically the fraction that you have of a given component of your atom relative to the total. So for instance, what the purple line is this is the fraction of neutral hydrogen. So what's the number density of neutral hydrogen divided by the total number density of hydrogen? And you'll see that as you get to, around, let's say 9,000 Kelvin, something like that, you start to get a pretty significant amount of ionization, and that's shown here. What we care about, though, here for the Balmer lines is not just neutral hydrogen. It also has to be in this first excited state, and it has to be equal to 2. So we can do that, and we find that the fraction of hydrogen that's in the n equals 2 state relative to all hydrogen is given by the green line, where I've multiplied this by a massive number because it's a really small fraction. Okay, so we can go ahead and then calculate for any given temperature what fraction of our hydrogen is neutral and in the n equals 2. We can do something similar and calculate a purple curve, but for calcium. And in this case, what I'm doing is I'm not plotting the neutral calcium to total, I'm plotting the singly ionized to the total. And so you see then your ionization increases, and once you're at 6,000-7,000 Kelvin, you're pretty significantly ionized here. So we could read off at for the sun, for instance, if we go to about 5,800 Kelvin, we could figure out what fraction of hydrogen's in the n equals 2 state, what fraction of calcium is singly ionized, and we can get these numbers. Okay. Just as an aside, why are they so different? The calcium becomes ionized at a much lower temperature than the hydrogen, and it's very sharp turn on. And that has to do with, in the Saha equation, that ionization energy. So you can look at the first ionization energy for many different elements, read it off for calcium, and plug it into your code, and calculate, for instance, the blue curve as opposed to the purple. Okay, so we know these fractions, so then we can take the ratio of those two fractions, and we find that it's like 6 times 10 to the minus 9. Okay, so what we want, though, is we want to know the number density of calcium relative to the number density of hydrogen. How much calcium do we have relative to hydrogen? So we can take the thing that we actually observed, that we have 400 more calcium-2 absorbers as opposed to these Balmer lines, this H-alpha absorber. So that's the measured thing. And if we divide this by the fraction of calcium that's singly ionized, multiply by the fraction of hydrogen that's in the n=2 state, you see this fraction works out to be the same thing here. And so that then is 400, what's measured, times 6 times 10 to the minus 9, and you get about 2 times 10 to the minus 6. And if you go back to the quick notes on simple atmospheres, you see the actual solar abundances, and you can see that this is spot on, which is pretty cool. Okay, so the last thing I want to say for the Saha equation is to note that it's not just for atoms. This comes up elsewhere in nuclear astrophysics. So the Saha equation, as it's written here, it refers to thermal equilibrium for ionization and recombination of ions. So you can absorb a photon and eject an electron to create an ionized atom. For nuclear physics, you can work out essentially the same relation, but instead for radiative capture and photodisintegration. So radiative capture means you absorb, for instance, a proton and you emit a gamma ray, and photodisintegration means that, for instance, you absorb a gamma ray and emit a proton. So similarly, you can be in thermal equilibrium, and the mathematics don't really care whether you're talking about ejecting electrons or ejecting nucleons. So it's essentially the same formalism, and if you want to see it worked out, you can go to my graduate nuclear physics lecture notes on astrophysical reaction rates, and you can see where this is worked out, more or less. Okay, so then if you write it down for nuclear physics, what you get is the following. The ratio of the number of nuclei to the radiative capture daughter, so in this case I'm assuming a P gamma reaction, is almost the same equation, right? You have 2 over a number density. In this case, you care about the number density of protons and not electrons. The mass here isn't the mass of the electron. Instead, it's the reduced mass between the proton and the proton capture nucleus. Otherwise, that's all the same. The degeneracy factors here are, here you deal with the nuclear spin, so it's going to be 2J plus 1 as opposed to the 4n squared that you use here. And then the energy isn't the ionization energy, it's going to be the energy required for the P gamma reaction to happen, or you can think of it as the energy required to eject the proton instead of ejecting an electron. And the equations are pretty much 1-to-1, right? Which is sort of cool. Now, one thing you may notice here is you might say, wait a second, for the atomic Saha equation, you have kind of the special thing on top and the normal one on the bottom. And here I have the proton capture, the nucleus that's going to do the proton capture on the top, and the one that has accomplished the proton capture on the bottom. So it might seem like these don't agree, or they're somehow flipped. But what you need to think about is in this scenario, you basically have an ion, it absorbs a photon, and that ejects an electron. Down here, you have a nucleus, it absorbs a photon, and it ejects a proton. And so that's why the one with the longer subscript is on the bottom in this case instead of the top. But essentially the same thing, which is pretty amazing. And this actually explains why in explosive burning scenarios, your nuclear reaction networks follow certain paths. So for instance, what's shown here is the chart of the nuclides. So each box has a different isotope, so different number of protons and neutrons. Number of protons increases in the vertical direction, number of neutrons increases in the horizontal. The lines here, the vertical and diagonal black lines, this is a nuclear reaction network path. So this is a sequence of nuclear reactions that happens in an actual state-of-the-art X-ray burst model calculation. And then I have very uglily pasted this on top of a chart of the nuclides, where the color indicates essentially the proton capture Q value. It's really the proton separation energy. And what you see is for these, this is for a type 1 X-ray burst on accreting neutron stars. This path, that's just known as the rapid proton capture process, or RP process, essentially follows the dark green boxes. And you can look here, the dark green boxes, that's around 1 MeV proton separation energy. So the RP process path, essentially, that's why it is the way it is you're in equilibrium for P gamma Q values of 1 MeV and below, which is kind of neat. And you can also do this, you'll see this worked out more often for the rapid neutron capture process, for instance, potentially in neutron star mergers. And there you'll enter in your environment conditions. Instead, you'll put in a neutron density and gamma Q value, and you'll find that our process for typical conditions is believed to follow neutron separation energies of something like 2 MeV until it eventually cools and falls out of equilibrium. And that is it for these quick notes on the Saha equation.